I'm Tom Campbell, a physicist, a consciousness researcher, and a citizen of an explorer of the larger reality. Today I'm going to talk about physics, existence, and everyday life. It's a little different than what I usually do, but I've been asked to put a little stress on the everyday life on this one. So we're going to spend a little more time talking about that. But I'm still going to drag you through the physics. I'm a physicist, and that's required. So actually, it's good to understand a theory. If you understand a theory, then everything else makes sense. Everything else, then, you can understand more easily. If you don't understand the theory, then you get little bits and pieces of it that seem to make sense, but you don't really know how it's all connected. So I think it's important to understand the kind of the science behind it. Okay, before I get started, I'd like to thank Donna Venny Warner and Keith Warner. Also like to thank Josh Myers and Dan Glenn and Unity North for providing these facilities. Because I'm just going to kind of hit the high points. I'm going to be making statements of this is how it is, but there actually is some science and derivation that gets to that point. I'm just not going to be able to give that to you today. There's just not that much time. It's hard for me to derive everything, in 4 hours. That's a lot to do. So we're just going to make a lot of statements here that are not particularly well supported because we don't have the time to develop the support for them, but there is places where you can go. You also can read the books for free on Google Books. I should have told you that before you went back there and bought a book, right? But they're free on Google Books, and they're free in a lot of other places. I've noticed that just recently doing a search. There's all sorts of places where you can get the books. Just download them, and that's fine with me. But, so you don't feel like that's, even though they are illegal copies, I really don't mind. So you can go ahead and download them from those places if you like. It's not a problem. Okay, I'll give you a very short introduction because if you haven't just kind of walked in here by accident and are getting this all cold, you will have already seen some videos. You're already aware of my background and where I come from and what I do. So I'm going to do that very shallowly. If you're not, and you want more on my background, there's a video out on YouTube that's a keynote address I gave at the Monroe Institute that basically goes into a lot of detail in my background with the Monroe Institute. But I'll tell you a very short version of that. I am a physicist. I did my thesis research in experimental nuclear, but I never worked in that field. After I got out of graduate school, I went to work in what I call the real world. That means the world other than academia. So working in the real world, it's all applied physics. And I've worked in various places. I started with technical intelligence, of all things. From there, I ended up supporting missile defense and doing other things in industry. In industry, you bounce around a lot. Jobs come and go as contracts come and go. So you do lots and lots of varied things. And now I'm a consultant. I've tried to retire several times. I'm actually getting close now. It's been probably 6 months since I've done any consulting work, and I'm hoping that stretches a little longer, but there are a few contracts where they are trying to get me to come back to work. So I probably still have a few working days ahead of me yet, but mostly I'm trying to retire and do other things with my time. So applied physicists basically solve real-world problems. What I ended up doing toward the end of my career and why they call me in as a consultant is I do very large, complex system risk analysis. So I worked with NASA for a while, for several years, and doing risk analysis for them, and I've done it through other industries. All the aerospace industries are in my neighborhood, and NASA has a big establishment there. So what that means is that you look at a big system, and NASA's a good example, and you have literally tens of thousands of piece parts made by 2,000 or 3,000 different producers, vendors they call them, of the equipment, and all of these things have to go together and then actually work. And they not only have to work, but if they have a man in it, it has to be safe. So they want to know what could go wrong and what's the probability of it going wrong, and if it does go wrong, how can you fix it? How can you keep it from going wrong? And if it happens, what's your plan B? What do you do then? How do you keep it from killing everybody on board and losing the mission and that kind of thing? So it's a very complex problem because things affect, the idea is you have this little thing that nobody cares about goes wrong, but it makes something else go wrong, which makes something else go wrong, and you go down this chain about 6 or 7, 8 levels, and suddenly there's a big problem. The whole thing blows up or whatever. It all started with this little part. So it's very difficult to do that with large things. So we do it with computers and we do it with simulations. So that's basically what I do that's my day job when I'm working. Now the other side of that, how did a physicist end up studying consciousness? I ran into Bob Monroe at a time when Bob was just beginning to want to take his experiences and legitimize them with science. Okay, he had had these experiences, they just happened to him. He didn't want them. He wanted them to go away for a while because he thought maybe he was losing his mind. Then he decided that they were real, there was something to them. Then he wanted to study them and make them science. So he just about got to that point where he had built this shell of a building and it was going to be the lab for the study of consciousness. I bumped into him about then and myself and some others became kind of his scientists that would help him make this into science. Our first job really was to find a way that we could induce similar states so people could have this out-of-body experience just in the casual passerby, have some kind of technology that could help them achieve that. And eventually we ended up with what's now called hemisync, which is a audio technology that puts people in what's essentially a good altered state, but it puts them in there and holds them there. So it's a stable, good altered state is what that does. So I worked with Bob. My deal with Bob was that I'll be a free scientist, but you need to be a free teacher and teach me what you know about the larger consciousness system and out of body and that sort of thing. So it was a good deal. I spent maybe close to 20 hours a week with Bob Monroe, him teaching me and others. A friend of mine, Dennis Menrick, with a double E. He and I were mostly putting the lab together. We built the equipment. We did the experiments on ourselves mostly. And so that was kind of how I got into consciousness. Once Bob Monroe had taught me how to go out of body, have that experience whenever I wanted to, basically on my own. And I came to the conclusion that it was real, just like Bob did. First you just wonder, am I making all this up? Is this just in my head? Is this my imagination? And then you do enough tests, you get enough evidence, you have enough experiences that can't be explained any other way. And eventually, unless you're in complete denial, you come to the conclusion that yes, this is real. It has to be real because look, I've collected all this data that you couldn't get any other way, and the statistical chances of that just happening by luck are 1 in 3 million or something. Then you have to say, well, something real is going on here. So being a physicist, what I wanted to do was find out, well, how did it work? What are the boundaries? What can you do in this larger conscious system? How does the conscious system interact with this physical system? How are they connected? What's my point in it? How are we connected in all of that? So that's what scientists do. They ask questions and try to find answers. At least that was my bent anyway. So then I spent the next 30 years, 35 years doing research, basically, doing experiments in the non-physical. Because you go to the non-physical, you want to know how it works, you go there and you do experiments. You see how things work, you look for consistency, you look for if you always do this, do you always get that? And eventually I kind of got an idea of how it worked, and that's where these books came from. The trilogy, My Big Toe, are basically the results from that 35 years of experimenting and fooling around in a larger consciousness system. So that's what I'm going to tell you today. I'm going to give you a little short run through of where the way I think it all works. It actually turned out to be more interesting than I thought. I started writing these books because somebody asked me. Somebody was over at my house and we were just kind of talking casually, and he says, "Well, Tom, how does this reality frame work anyway? Tell me, what's the core? What's going on here?" So 4 or 5 hours later, I realized I really needed to write it down because it was hard putting it all in words and making sense of it. So that's when I started writing. And my first version of the trilogy was 8 pages long. And I thought I was done. And I passed it out to a couple of people and said, well, here it is, I'm done. And they read it and said, what? What does this mean? So I said, well, okay, I'll elaborate a little bit. And I elaborated a little bit. And so it went through this process of do you understand? No. Would you please elaborate? And me elaborating. And I ended up with, first I said, oh, I'm going to have enough material here for a book. I didn't intend to write a book. And then it was way more material than I could put in a book. So that's how the trilogy really got started. And I was explaining the larger reality and how we connect to it and how the physical reality is created through it. But I really wasn't doing science because I was just doing the larger reality. I wasn't really trying to do physics with it. And then afterwards, I had it written, and I looked at what was, I kind of took a step back, took a bigger picture, and it kind of came to me that, gee, this is good science too. This starts to explain things that right now, are big problems in science. So the more I thought about that, I started becoming the physicist more in it. The more I thought about that, I realized that it explained all of the big questions that is facing physics right now. We have this problem with, Einstein worked for a long time on a thing called unified field theory. He was trying to take quantum mechanics and relativity. Now, I make everything derived from physics. I'm a physicist, so you have physics as the big thing and everything else grows out of that. But what that means is that physics basically is your fundamentals of reality, right? It's your particles. It's all your little subatomic particles and then atoms and molecules and all of the stuff. And everything else is built on that. So biology really, in a physicist's mind, is an extension of physics, right? It just takes aggregates of those particles and what they do. And so is everything else. So when I talk about science, you'll hear me say physics, but I'm really talking about all of science. It's more general than just what you might think of as physics. So anyway, I realized that what I had written, the same general theory that explained reality, also explained why the speed of light's a constant. That's a big problem. If you know that, you can derive relativities, special relativity is just a little algebra problem after you understand that light speed is constant. That was the assumption Einstein started with. Why particles ought to be probability distributions. Okay, that's the big problem with quantum mechanics. Quantum mechanics starts with that assumption. Particles are probability distributions, but they have no idea why. Why it ought to be that way, they don't know. All they know that if they start with that assumption, they can use mathematics to produce answers that then predict what happens in experiments. So it works. Very successful branch of physics. Probably the most successful branch of physics. So they don't know why particles ought to be probability distributions. Well, this then explains why they ought to be. We have other problems in physics like where did the Big Bang come from? What happened before the Big Bang? You've probably all heard of Big Bang cosmology theory. And this explains that. Where we have a physics problem with our universe is expanding. It's not only expanding, but it's accelerating. And physicists ask, well, what's it expanding into? What is that out there that we're expanding into? And where does all this extra volume of space come from and so on? And of course, these are unanswerable questions because they have the wrong concepts to begin with. That's why they can't answer them. Once you understand the my big toe theory here, then all those answers just fall out. So it starts to do good physics. And on top of that, there's things like PAIR labs. PAIR is an acronym. It's Princeton Engineering Anomalies Research. And out of Princeton, which is a pretty strong physics house, that's where Einstein did most of his work in his later years, they have a group there that studies these anomalous things. Well, basically, that's mind-affecting matter is what they studied. And they were able to have people who could use their intent to change the way experiments came out. And they've worked on that for years and years. And of course, they have all this data, and all the stuff, and oh, it's 1 in a million that this could happen by chance, and so on, but no theories as to how any of it works or why it should be that way. And we have things like the placebo effect. Everybody knows what that is. You give people sugar pills, tell them it's wonderful medicine, and they actually get better compared to a control group that you don't tell them anything. And another control group, I guess, that you actually give them the medicine. Matter of fact, it's such a credible concept, this placebo, that it's what's required in order for a medicine these days to be marketed. If you can't beat the placebo effect, if your medicine can't do better than a sugar pill with good intent, then you can't sell the medicine. They say it's not effective, and that's not necessarily true. And that placebo effect, by the way, is getting harder and harder to beat. We have drug companies now going offshore, going to third world countries in order to do their research, because the placebo effect is easier to beat there than it is here. And then they can then sell them because there's no rules that says where you have to beat the placebo effect, just that you have to beat it. So you can take it to other cultures that are simpler than ours. And the placebo effect is a little easier to beat. Anyhow, that's kind of a long introduction. I want to start today by kind of telling you the bottom line, where it is that we're going, and then we're going to back up and see how it is we got there. That way, because I'm compressing this so much, I want you to kind of have the end point in mind, which will help make it make sense as we go through it. Physics evolves through a series of revolutions, and they tend to act like this. You have the old paradigm, and everybody thinks that's the last. We know it all now. This is our paradigm now. That's the old paradigm. Then a bigger picture comes along. They see in the bigger picture, the old paradigm becomes a subset of the larger paradigm, the bigger idea. It doesn't go away, it just becomes a subset because it really did work within a certain area. It's just that they didn't have a big enough picture. Okay, now so here's some examples of this. Obviously, we have first flat Earth, right? And then we had spherical Earth. Well, you have a bigger picture with the spherical Earth, right? But the flat Earth didn't go away. All the surveying that's done now, the surveying for homes and whatever, it's all done on a flat Earth model. If you have short distances on the surface of the Earth, flat Earth is very good. You don't have to worry about the curvature of the Earth if you're just laying out a few acres someplace. That curvature is in the 7th and 8th decimal place and really doesn't make any difference. So flat Earth is a good approximation. Another example would be Newtonian physics. When Newtonian physics was around, we thought we knew everything about physics and how the world worked. It was this big clockworks and everything was kind of, very mechanical and mechanistic. That's where our idea of objective reality came from, really. It was the Newtonian model. Well, then came along relativity and quantum mechanics, and they said, well, the Newtonian model is just wrong. It's the wrong answer. But if you're in the macro world, which is the world of big things, and if you're not going too fast, it's a very good approximation. Wrong, but a good approximation. So we keep doing this. We get a bigger picture, the old becomes an approximation. Well, what's happening now is that quantum mechanics and relativity are now being seen as a subset of something bigger. Now, most physicists probably wouldn't agree with that because it's early in the stages of this, but it's been doing it for probably, at least 2 decades now. We've been growing toward accepting this bigger picture, and that is of reality is information, just information. So we're getting away from reality is volume, space, mass, that kind of stuff, into reality is just information. I know it sounds strange, but that's basically where it's going. That's the trend. And that's not just me and my big toe, but that's basically science in general. It's been moving that way since about the 1990s, late 1990s, when Edward Fredkin, still a powerful physicist today, came out with his digital physics movement. And that was based on this idea that reality is computed. It's information. And that's been gaining ground. And the reason it's been gaining ground is it's better physics. It answers more problems, just like the round Earth answered more of the problems than the flat Earth did. And quantum mechanics and relativity could answer more problems than Newtonian physics could. Well, this reality as information answers a lot more of the problems of physics than reality as objective, which was really the old Newtonian view, does. So it's better physics. So eventually, you see, it keeps growing, and people are working toward that direction. So that's kind of where we're going. And I was really glad to find that, because I had already written my books and had them to the very last chapters when I found all this out. I didn't run into Fredkin until I was already, ready to publish, and I said, well, people are supposed to do these literature searches before they start, but I did mine at the very end. And then I found there were all the digital physics movement and the rest of it that I wasn't aware of, because I'd been out of academia a long time. And I thought, yes, that's where they're going. That's the same place I had gone. So, okay. Now, the objective reality that we have now, our current physics is the reality is objective, that will become a subset. Okay, what's its criteria for being a subset? In those areas where the uncertainty is small, then reality will be approximately objective. Where the reality is large, it's not. Your reality as information is based on probability and statistics, period. It's not an objective reality. Okay, so for example, if you had if you have an electron, it's a very small thing, we can't really see it, we just assume that it exists. Actually, it's an inferred existence. There's a difference between what a thing is and what a thing does. We look at the results, we look at the, we look at phenomena, and from that we infer an electron. It's just inferred. That's why we get so surprised when it turned out electrons were probability distributions, because in our minds we begin to believe our inferences, you see. So we measure effects. Here's the effects. We measure them and we say, well, those effects look like it'd be done by an electron. You see, so then we believe that this electron exists, but all it is an inference from the effects. Okay, and that's an important distinction. The effects of a thing and the thing itself are different. The thing itself is not its effects. All we ever measure is the effects of little things like electrons. But anyway, where I was going with that is electrons. Where is this electron? Well, it's small and it moves very fast. Or where is this photon? It even moves faster, right? Where is this photon? Well, there's a lot of uncertainty because it's so small we can't really see it. It's just an inference, and it's really moving very fast, so we don't know. So it has very big uncertainty. That's why it shows up as the thing that kind of violates the idea of a objective reality. And I'm going to show you that in a minute with the quantum mechanics experiment called the double slit experiment. So that's the thing that's small, but take a baseball or a cannonball or something, and when we can track that, we can compute where that goes, down to 6 or 7 decimal places. There's very little uncertainty with it. So that's an area that has small uncertainty, and that's where then the objective reality applies, approximately, but only approximately, okay, because everything is really only probable and statistical. Even cannonballs, even this room. If we had a team of 10 different scientists come in and say, what's the volume of this room? Well, they'd all agree to the first 2 or 3 decimal places, but after that they'd all disagree. Why? Because the volume of this room is really not an objective quantity. We think it is, but it's not. How do you measure what the volume is precisely now? We're talking about not just approximately, but precisely, when the walls are all dimpled and they all have, these aren't flat. They're not perfectly flat surfaces. They're all rough surfaces. The floor is a rough surface. The ceiling, you can tell, is a very rough surface. How do you know just how tall it is when you have all these dimples and valleys and stuff? And then you get down to molecular level, and all of these surfaces are in motion. They're not even standing still. The surfaces are doing this. They're coming and going, and particles are flying out of them, and other things are coming in. It's totally a dynamic situation. There is no volume of this, period, an objective volume. There's only an approximation. And that's what we say. We say the volume is, X plus or minus, Y, some amount. Everything's like that. There is nothing that's objective. Now that's just talking about measurement error. It's a lot more fundamental than that, and as we get through it, you'll see that there's more than just the measurement area that we're talking about. So the next thing that's happening is that physical reality is going to be explained as virtual reality. That's going to be step one, but that's only the first step of two major paradigm shifts. Now that's going to be a pretty massive paradigm shift, isn't it? That actually this is a virtual reality and it's computed, but that's where we're going. After that, we're going to have virtual reality is a product of consciousness. That's the second step in this. So we're going to have two major paradigm shifts there. And that makes the physical reality then a subset of what I call the larger consciousness system. Okay. Now, consciousness then is fundamental and everything else is virtual. So that means all of the reality frames are virtual. This one's virtual. Physical reality is virtual. Your dreaming reality is virtual. Where you end up after you die here is virtual reality. Where you go when you remote view and go out of body, that's a virtual reality. They're all virtual realities. The only thing that's fundamental is consciousness itself. This is a double slit experiment, and I'll do it real quickly. It's a very famous experiment. This experiment has probably been done more times, more places, by more people than any other single experiment in the history of science. And it's because it gives such strange results that everybody wants to do it and see if it works like that for them. So this has been replicated over and over and over again, and whenever done properly, it always gives the same results. It tells us something very important about the nature of reality. And just as the Greeks told us, like 200 years before it was accepted that the earth was a sphere, the Greeks told us it was a sphere. It's not that hard to go. You know that the phases of the moon has to do with the shadow of the earth on the moon, right? And what's that shadow look like? Not a straight line like you get, it's a curve like a sphere, right? That's what that's pretty obvious. When a ship goes off and sails, it doesn't just go out until it disappears into a spot. It sinks. You see the whole ship, then you see the middle of the ship, then you just see the top of the ship, and the last thing you see is the flag on the top of the mast, disappear. Why? Because it's going down around a curve. So we had some basic, measurements, if you will, that said the Earth's a sphere. But for 200 years, people said, can't be true. Just can't be true. It just doesn't make any sense. If the Earth was a sphere, all the water would run off the sides, and there wouldn't be any oceans. And everybody and everything that was on the bottom side would all fall off. So that was the reason why it just didn't make any sense. It was a ridiculous idea, the Earth being a sphere. So for 200 years, we knew that it acted like a sphere, but nobody could believe it actually was the way it was because it just didn't make any sense. Well, why does that happen? They were ignorant of a very important thing called gravity. Right? And once they got the concept of gravity, then the Earth being a sphere was no longer impossible. So there was a flaw in our concept. That's the way this double slit has been. So now we're almost 100 years, actually about 90 years, past the time when this experiment was first done, and heads are still firmly in the sand because, well, it just doesn't make sense. This experiment doesn't make sense, and there has to be some other explanation. Physicists today simply call it intractable weird science. That's all. And they've given up on finding a bigger picture, understanding of reality in which this experiment does make sense. The thought now is, it's impossible. Nobody will ever know. That's the way they approach it. Okay, well, we're going to show you, and you'll all know. Maybe they won't, but you will. Here's what happened, and I'll show you why it is such a famous experiment. Early on, we knew that waves, if you had a wave came to this thing, we have a barrier, a hole, a barrier, and a hole. That's called a slit. And it's two of them. There's a double slit. That's where the experiment comes from. That if a wave came here, some of the wave would go through this slit, some of the wave would go through that slit, and the distance from here to here is a little shorter than it is from here to here, right? We can see that. That's pretty obvious. If that difference in distance turns out to be like this, so the wave coming from the top hole and the bottom hole are shifted in distance, one whole wavelength, then they both dip at the same time, they both crest at the same time, they add together, it's called superposition, and you get a spot of light there. But if they happen to be just that difference in distance, where one gets to a peak just as the other one gets to a hump, you add them together, you get nothing. That's why you get nothing there. So what happens is you get this series of spots. It's called a diffraction pattern when you have waves going through the two slits. And that had been known for several decades everybody was happy with that until Einstein was doing some work with the photoelectric effect, and he says, you know, light comes in little particles. It's discrete units of momentum. Therefore, light's a particle. We'll call it a photon. And people said, well, if it's a photon, then we ought to get this because it's a particle. You know, particles go through a slit. What do? They go straight through the slit and they hit a spot right behind the slit because a particle always travels in a straight line unless interacted by some exterior force. That was Newton's maybe second law. Okay? So there was a problem now. This didn't look like particles. That looked like waves. And this didn't look like waves. So which was it? So they did this experiment with the double slit. They found a way to just fire one photon at a time at the slits, a particle. What they expected to see was this. What they saw was a diffraction pattern. Okay, now that was a surprise. They didn't expect that. So they said, well, there's something funny going on here at these slits. So these little red things are detectors. And they said, we're going to put detectors there at these slits and we're going to see what's going on. And they did. They detected every time a photon went through this slit, this detectors would say, you know, it went through the upper slit, or the detectors would say it went through the bottom slit. And whenever they did that, they got this pattern. So now the problem was, we take the detectors away and you get this pattern. Then the idea was those detectors, they're doing something there. But they found out, and these are called quantum eraser experiments, they found out that you could take this data with these detectors, take all the data, detectors are working, it tells you exactly what slit each one goes through, but you don't look at this data and you don't look at that data yet, you just take it. Now if you look at it, you'll get this. But if you don't look at it and then you erase this information of which slit they went through, you get this again. You see? So obviously reality is not objective. That's the double slit experiment, and that's why this is such a big deal, because it shows that reality is not objective. There's something else going on here. So that's really what happened. Now I'll tell you how it's explained. They came up with an explanation that the photon isn't really a photon, it's a probability distribution. And why? Because they looked at here at how these spots were arranged and they said, well, that kind of looks like a probability distribution. That they have certain probability of going these various places. How else can you explain a particle ending up in these places other than it has a probability that it goes here and then a zero probability there and a little more probability here and so on. So that was the scheme for coming up with this. And so here's a part of this probability distribution. It really goes from 0 to infinity. The probability distribution goes out over all space. And the idea was that some of the probability went through this slit and some of the probability went through that slit, and the probability waves combined in order to produce this diffraction pattern. Well, of course, most of the physicists looked at that and said, you know, that didn't really make intuitive sense. But in fact, this turned out to be such a powerful method that it turned into quantum mechanics. And this is the basis of quantum mechanics, is that particles aren't really little massive particles, they're just probability distributions. And what happens here is that when you measure that a particle came through here, what physicists would say is that the measurement causes the probability wave to collapse to a physical particle. That's the way, you know, Bohr would have said it, or Heisenberg. So what happens is the idea that you measure it here makes this probability distribution turn into a particle. Once you have a particle, the particle can do nothing but what particles do, which is travel in a straight line. Now, there's another thing that you often hear in physics about the measurement problem, and that's what they're referring to. That measurement creates the particle, but that's not really the case. It's not a measurement problem. Sometimes you hear that consciousness creates the particle, but that's not the case either, because it takes a consciousness to make a measurement, right? I mean, even if the consciousness gets a machine to do it for him, it's still, you have to have a consciousness in the loop someplace. Okay, so, but that's not true here. That's just, it's close, but it's sloppy language. Okay, the key ingredient is neither consciousness nor measurement, though both are involved. It's the availability of information. It's the availability of information. If you have information about which slit a particle went through, then you know that there's a particle there. That means it has to act like a particle. If you don't have any information about which slit it went through, then there's not a particle there. You don't know that there's a particle because you haven't measured one. If you don't have that information, then you get this. What's going on here is that you have a virtual reality composed based on information, and that it needs to be a consistent reality. You can't have things being two ways. You can't have, when we walk out that door, we're going to be in Atlanta, but sometimes if we walk out that door, we're going to be in Minnesota. That doesn't, you can't have inconsistencies like that in your reality. Things have to be consistent from time to time, second to second, all the way. So we have a consistency problem in a reality based on information. If you have information that this is a particle, you have to get a particle. If you don't have information that this is a particle, you don't get a particle, you see? So it's just a matter of consistency within a virtual reality based on information. All right, so that's what's going on. So it's not consciousness that collapses. It's not really the measurement that collapses. It's the availability of information that can create an inconsistency. Once you have this information, it would be where it slit the particle went through, it would be inconsistent in this reality to end up with a diffraction pattern. You see? So that's really what's going on there. And now they've done, like I say, they've done these delayed quantum erasure experiments. The last one that I have seen done was published in the year 2000, was done in 1999, was a brilliant experiment that kind of solved all the problems people had with this. Part of the problems that people had, they say, well, when you detect this particle here, you actually have to hit it with some energy. Otherwise, you can't detect it, right? You have to interact with it somehow. And somehow that interaction is really what collapses the wave function and produces this particle. Well, that's not true, because otherwise you wouldn't have this erasure, the ability to do the erasure where you collect the data, which means it's being interacted with, and then you erase the data later and you end up with the diffraction pattern. So we know that really wasn't true, but most physicists who aren't quantum mechanics theorists still believe that there's something here that interferes with that particle and whatever makes it, because otherwise they can't, they can't deal with it because there's no explanation. It's just that weird science. So that's still a common belief. Believe it or not, that's still a common belief. But this experiment I was talking about that was in 2000, they did a really neat experiment where it was no touch. They measured which one it went through without ever touching it with any energy. And it's a really elegant experiment, but I don't have time to get into it now, but the touchless thing has happened. Also with the erasures, the experimenter had to go in and kind of do the erasure and not do the erasure and see the difference. And in this elegant experiment, the erasure was all done by quantum mechanics itself. It was all this probability. But it was a delayed erasure, which means after the data was already collected, then they erased it, and then they got the diffraction pattern instead of the pattern that they would have had. We'll go over that a little more. That's what we want to talk about. Well, I will give you a little experiment that I'm going to make up. This is not an actual experiment, what I'm going to tell you. This is just a logical equivalent, so it's easy for you to follow and understand. Actual physics experiments are very complicated, and they're very hard to explain, but this is, like I say, a logical equivalent. Let's say that we take 102 of this experiment. In other words, we're going to measure what slit it goes through, and then we're going to keep track of what happens over here on the screen. And we're going to do that just 102 times. And we're going to take data for an hour. put that in the computer, take the data again for another hour, put that in. And what we'll do is the first one we'll take this data, put it in an envelope, call it detector data, experiment 1, and we'll take this, put it in another envelope, call it measurement screen data, experiment 1, put those 2 envelopes into a big envelope and call it experiment 1. You with me with that? So I got an envelope that says experiment 1, and I've got, inside that, I've got 2 envelopes. One of them says detector data for experiment 1, the other one says measurement screen. So I've got all my data in here. So that's just an easy way for us to keep them straight. So we're going to do that 102 times, and because we're doing this experiment, we always expect that as the result. So after we have 102 of them, we look at the first one we did, and we take this data out of the envelope, take that data out of the envelope, and this is exactly what we see, just what we expected. That's the experiment we're doing. And then we take the last one we did, and we do the same thing. We want to make sure that they're the same, right, on both ends. So we do that, and we get exactly this. You know, we get the 2 spots of light here, is what we get. So the first one and the last one are like that. We assume all the ones in the middle were like that because they were all just done together. All right, but now what this delayed quantum erasure means is that let's take the 100 envelopes that are left, right? We got rid of number 1, we got rid of the first one and the last one. Now we have 100 left out of the 102. We'll take those 100 and we'll shuffle them, we'll randomize them up. Then we'll deal them out into 2 piles of 50. Now, one pile of 50, we will look at them. We'll take the envelopes out and look at them, and every one of them, all 50 of them, will look just like this. We have the 2 spots here. Now the other 50, we'll take out the detector data of each one of the 50, put them in a pile, and set fire to them. We're going to burn them. We're going to destroy them. That's our eraser experiment. Okay? I'm making a very simple concept in the eraser experiment. We just burn them and destroy them. And no, they're not still readable in the ashes. We'll take the ashes and put them in water or something. Don't complicate the experiment. We're just going to burn them. That's going to get rid of them, and they will be erased. And then we'll open up these envelopes, and every one of them will be a diffraction pattern. You see? That's what I mean by a delayed quantum erasure experiment. Every one of them will be. And you're thinking, how could that happen? You see, the experiment was done, let's say, a year ago before we took these envelopes out and sorted them. It doesn't matter. 10 years ago. The amount of time is irrelevant. In these experiments, they're actually done like 10 nanoseconds. But it doesn't matter. If you can do it in arrears, you can do it any amount of time. So that's why this is weird science. It looks like, depending on what you do with this data, you make this change from this output to that output, right? That's what it looks like. But that's just because you believe you live in an objective reality. You see, in a statistical probability reality, this is still indeterminate. It hasn't happened yet because you haven't looked. You see, you don't know what it is. In an objective reality, you know because you did this experiment, that's what it had to be. So you believe that's the way it is, and then you somehow magically changed it to this. Well, there's no magic involved. It's just that because this data hasn't been looked at, it doesn't really exist yet in this reality because we live in a probabilistic reality. I know you're thinking, that sounds impossible, but that's because you are ingrained from your culture with the concept of an objective reality. You believe that's the way it is, so when you see this or hear about it, it just doesn't make sense. Just like the world being around didn't make sense, because all the water would fall out and people would fall off. So this doesn't make sense because you're used to an objective reality. Well, that's not what we have. A little fact we talked about, I introduced this earlier on. Objective reality really comes in 2 statements. And this is Newtonian's viewpoint. Objects exist, A, locally and independently, and B, within an absolute space and time. That's Newtonian physics. That's when the world worked like clockwork. All right. Now here's the rub on this, and this is why Einstein and others really wanted to try to combine these 2 sciences, relativity and quantum mechanics, with some overarching. Why did they think there was something overarching? Because quantum mechanics requires that B is true and A must be false. Relativity requires that A is true and B must be false. You see? That's a problem. So obviously, Einstein's view and others said they can't, these two things can't be fundamental. There must be something more fundamental above them that says that quantum theory, says that A is false, and relativity says A must be true, and vice versa. So they're fundamentally incompatible with each other, yet they're both exquisitely successful scientists, and all their measurements that they do work, but one works at very big scales, high speeds, the other works very tiny scales. So they both are just subsets. Neither one of them works outside of their little subset. Okay, so that's just an interesting fact there. Now let's take a quick historical perspective. Einstein, working on his unified field theory, trying to bring these two together, some overarching theory. Here's some of the things he said, and I'll just kind of read the words that jump out at me. He basically came to the conclusion that space doesn't have an independent existence. Starting to sound like virtual reality, doesn't it? That's what you'd say if this was a virtual reality. Reality is merely an illusion. Sounds like virtual reality. Sounds like Buddha, right? The space of physics is not, in the last analysis, anything given in nature independent of human thought. Oh, now space is not only, an illusion, but it's a function of mind. Okay? And then here's one. After working in this for a very long time, he and David Bohm worked together on this field theory for a long time. And Einstein said, one has to find a possibility to avoid the continuum together with space and time altogether. But I have not the slightest idea what kind of elementary concepts could be used in such a theory. You see? Double slit experiment says it's not, we have a probabilistic reality. Particles don't really exist, they're just probability distributions. And we have these two things that disagree with each other, the relativity and quantum mechanics. Einstein works on it for 25 years, fails, because he just can't figure out how to get a hold of it. He doesn't know any way to state it or to make any theory about it or anything. So it just is weird science, you see. Here's some guys that worked on quantum mechanics. These are kind of some of the founding fathers I'm quoting here, and I'm going to be quoting Nobel Prize winners. Everybody I'm going to show here and quote are all Nobel Prize winners in physics. Scientific conclusion that the content of consciousness is the ultimate universal reality. Funny statement for a physicist to make, isn't it? Particularly one of the founding fathers of quantum mechanics. Max Planck, another one. This is very interesting because he talks about we ourselves are part of the mystery that we're trying to solve. Well, that's much like Einstein said. What's out there in the physical world is somehow entangled with what's in here, but we don't know how. So consciousness is at the root of this reality, but I don't have the slightest idea, what kind of, fundamental things that I can base this theory on. Okay, now here's quantum mechanics. Werner Heisenberg and Niels Bohr were two of the inventors of quantum mechanics. They were two of the big guns that produced this science. Okay, Heisenberg, the only thing he can accurately describe an elementary particle is a probability function that in itself contains nothing about the quality of being of the physical existence of that particle. So he's saying these probability distributions, it's not just that, well, there really is a particle somewhere and we just don't know where it is, and here's the probability distribution. That's not what they're saying. They're saying there is no particle. The particle is just probability. Okay. Niels Bohr, common sense view of the world in terms of objects that really exist out there, means out here in the physical world, independently of our observations, totally collapses in the face of the quantum factor. That meant in the face of the double slit experiment at that time. And I like this one. If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. Every great and deep difficulty bears in itself its own solution. It forces us to change our thinking in order to find it. Okay? What he's saying is that we realize Newtonian physics is wrong. We realize that relativity and quantum mechanics are just both looking at a piece and that there's a bigger understanding. We realize that objective reality is wrong. It's a probabilistic reality, And we need to come up with a better, bigger viewpoint, a bigger picture, a new paradigm in which it makes sense. That's what they're saying, you know. Challenges our thinking. Okay, we're up against the wall here. We need something new. And then there was Einstein saying, new? I have no idea, you know, what I can come up with that's new that'll do this. Okay, another one that Einstein said, I don't have it listed up here, he says, no problem can be solved from the same level of thinking that created it. All right, what he's saying is that if you can't find a solution, you need a different paradigm. Okay, your belief system has put your solution outside of the space that you realize exists. You know, your solution's somewhere else. You need to think. You need to change your focus. So we saw there that the quantum mechanics theorists back in the middle 1920s were all very excited about this new paradigm that was going to come about, and we would have a whole new view of reality. Newtonian physics would finally be dead, and instead of quantum mechanics was half Newtonian and half, you know, beyond. Relativity was half Newtonian and half beyond. Each one had one of those Newtonian assumptions in it. Okay. 1920s, mid-1920s, brave new world, new paradigm. We're going to march on to a whole new era. Well, here's where quantum mechanics is today. And I'm quoting Richard Feynman, not because I want to pick on Richard Feynman, but Richard Feynman's a good example. He is one of the best. He's dead now, but he was a very good physicist. His specialty was quantum mechanics theory. He was a brilliant guy. He also, I think, had Nobel Prize. And very competent guy. So he's the best. I'm not picking on some quantum theorist that nobody ever heard of who said a lot of foolish things. This is Richard Feynman, who knew exactly what he was talking about. He says the double slit experiment contains the basic mystery of quantum mechanics. True, it does. He also said, shut up and calculate. And who he was talking to when he said that was his graduate students. Said, Dr. Feynman, this doesn't make any sense. What's going on here? This is absurd. It doesn't make sense. And he said, shut up and calculate. What does that remind me of? That reminds me of the, you have these fundamentalists who say that they couldn't have dinosaurs and things like that because the world's only 7,000 years old. And, so they have some, I can imagine some young student in their care that says, yes, but Reverend Sir, the world is millions and millions of years old. It takes suns 10 million years just to coalesce, and our evolution goes over hundreds of millions of years. And the Reverend says, shut up and pray. Yeah. Fundamentalism is fundamentalism wherever you look at it. This is fundamentalism in physics. Shut up and calculate, right? He also said, quote, I don't understand quantum mechanics. He was an honest guy. He knew his stuff. Quantum mechanics represents a phenomena that's impossible to explain in any classical way. Well, what does that mean in any classical way? That means in terms of objective reality. That's what that means. So it's impossible to explain. So you see, we went from the physicists in the 20s saying, brave new world, all we need is a new paradigm, to it's impossible. There is no new paradigm. Now, it's not that these are just kind of wimpy physicists who give up easily. Einstein worked on this problem for the last 25 years of his life, and he came up empty-handed. There's not very many scientists or physicists or any kind of people in academia that can go for 25 years and not publish anything, come up with a failure, and still hold on to their jobs. Most in the publish and perish world, if they hadn't published in a couple of years, it's out the door. Or if you have tenure, it's sweep the floors. You're no longer important in that world if you don't publish. And this was a dead end because nobody could figure out, like Einstein said, I don't have any idea where to go with it. So the physicists aren't stonewalling here, they just don't know what to do, is the problem. Harrison, and it's because I gave this in Canada, I picked one out of the Department of Physics in Toronto. I could have picked one out of the Department of Physics in any university anywhere in the world and said the same thing. This is standard attitude. It may be true that nobody can understand quantum mechanics in the usual meaning of the word understand, which means in terms of objective reality. So that's where we are today. Basically, can't be solved. Weird science, don't know. Okay, so that's the end of it. Why are we there? What's the big problem? You know, Feynman knew quantum mechanics as well as anybody knew quantum mechanics. He just couldn't bring himself to say, at least not in public, that reality was not objective. And instead he said, shut up and calculate, and I don't understand quantum mechanics. The problem here is that the whole premise of science is based on this jewel called the scientific method. Right? Scientific method is what delivered us out of ignorance into light, gave us projectors and laser pointers and all this kind of stuff. So we believe that, but it's wrong. See, the scientific method depends on reality being objective. That's its whole, that's its fundamental basis. It came out of the Newtonian period that reality is objective. Therefore, anybody can form any experiment anytime, and it always has to come out the same. That's what the experiment method says. Well, that's not necessarily true, but it is true in this special subset of reality where reality is approximately objective, and that's where the uncertainties are small. Now notice physics is already moving, it's already separating itself out in that direction in the sciences. What do we call the hard sciences? The hard sciences are the sciences that study things that have small uncertainties. See, hard science is the stuff where you can measure down to 6 decimal places, right? You don't have a lot of uncertainty. Well, what are the soft sciences? They're sociology, economics, psychology, right? Those kinds of things where, even probably anthropology, other things where there's lots of uncertainty. You don't know. So because you have that uncertainty, the scientific method doesn't really apply to you unless you try to get rid of that uncertainty. What do social scientists do to get rid of uncertainty? They do double blind, triple blind, because they know that if they don't, the fact that the experimenter himself knows what the experiment, what's going on in the experiment, that it's not double blind, will change the results of the experiment. What's that? It says mind, understanding, information, changes the result. Well, that's not objective. It doesn't happen in an objective world. Placebo effect can't happen in an objective world. Well, the world's not objective, you see. So we're already seeing that the hard science is kind of separating itself into those areas where what it deals with has low uncertainty. How heavy is this? How fast does that go? That's the world of physics. What happens when you put these two chemicals together? Those are approximately objective. Contemporary science. I told you that physics has been moving toward virtual reality now for a while. It started with Fredkin, 1992. Basically, Fredkin said reality is essentially digital and informational. And as soon as he said that, somebody said, well, if it's a computation, if our reality is really a simulation, then who's doing the simulation? Who's simulating? Who's the programmer? And Fredkin said in his paper, this is a scientific paper presented in scientific colloquium kind of thing, other. He said it's computed in other. That's kind of a cop-out, right? Because he didn't know what else to say. So it was just other. Well, other, you see, is consciousness. Consciousness is a digital information system. This is a virtual reality. So that's where we're going with all of this. Bostrom, he has a degree in physics and a degree in philosophy. He's now head of a department at Oxford. So not a lightweight, somebody with some reputation and a smart guy. He wrote a paper that was now pretty famous, You're Living in a Computer Simulation. His bottom line was, it's likely that we're all living in a computer simulation. Okay, so he said, that sounds like a very likely thing. Brian Whitworth, basically he is a computer scientist, not a physicist. He said, okay guys, we've got this virtual reality theory here, we've got this objective reality theory here. I'm a independent agent. I'm a computer scientist. I really don't care which one of you, right? I just like to know. So he did this big matrix and he says, here's all the things we know, all the experimental facts in the world, and here's what reality is objective, how it answers that mail, and here's how reality is virtual, how it answers that mail. So he went down through it all And at the end, he said, physicists, you need to wake up. A virtual reality is better physics. It answers more of the things we know and has fewer problems than reality is objective. Has more problems and doesn't answer as many questions. And Brian's papers are continuing. This is just one he did some years ago. He's then published 3 more since then. He's really working on the mechanics of virtual reality.